I want to start off today's lesson with just a couple review problems dealing with the uses of I. So if we have a negative and a root, we learned that we can simply correct that issue by using an I to represent square root of -1. So root -9 is really just 3I. And then we have our positive 9, and we learned also that I squared is equivalent to -1. And then we just go through and we see if we have any like terms. So obviously 9 minus -1 is 10. So my answer is 3i plus 10. For root -98, again, the negative simply means I'm going to have an I in my answer. And other than that, I can kind of just ignore it and deal with the 98. So I know that 49 times 2 makes 98. And the square root of 49 is 7. And I'll just have to add in the I because of the negative. So I'll have 7i root 2 as my answer. For number 3, probably want to deal with the root 12. That can be simplified, and we want to make sure we always have all of our radicals simplified before we go ahead and combine like terms. So I know that 12 can be written as 4 times 3. And I'm going to put the negative with the 4 because that's going to become a whole number. So we'll go ahead and change root -4 into 2i. And then my new problem now is 5 times 2i times root 3. The 3i root 3 does not simplify, so we're going to leave that alone. But we can go ahead and combine -2i and 8i to make 6i. So if I do this math real quick, I know 5 times 2i is 10i root 3. And so what I have here are like terms. 10i root 3 plus 3i root 3 is 13i root 3 plus 6i, and that's about as far as I can go. For number 4, we want to change our I squared to -1. And so it becomes a very simple problem, back to probably this more simple math that you're used to. So we get 8. Now, if you look, number 5 and 6, they look like they're almost the same problem. And I'm doing this on purpose because I want you to see just how different the workload is for each problem. We're supposed to take these quantities and multiply them together. Whereas in number 6, we're adding the quantities together, not multiplying them. So that's going to kind of change what we do. So we will have to FOIL for this. We're going to have to do 9 times 2 and 9 times I. And then we'll have to do -3i times 2 and -3i times I. -3i times 2 would be -6i. And -3i times I is -3i squared. And then we're always going to have some cleaning up to do. We know we can do 9i minus 6i, and that makes 3i. But I also know that I squared is -1. So I want to change that as well. So if we simply do -3 times -1, this is really going to become a +3. So if I have 18 and 3, that makes 21. So my answer is 21 plus 3i. In number 6, because it's an addition problem, the parentheses don't serve any purpose. There's no order to have to worry about when you're doing addition. So we can drop the parentheses. And we're just looking for like terms. 9 and 2 can make 11, and -3i and I can make -2i. So my answer is 11 minus 2i. So the workload for between 5 and 6 is quite different. So that plus that's in the middle really does change how much work you're going to have to do in the problem. All right, so those are all things that we've already done using imaginary numbers. So today I'm going to just present a couple different scenarios to you. And that way you've kind of seen all the scenarios you're going to be faced with involving I. So I have an equation that says 50 plus 9i. You have to remember 9i is a number. It's an imaginary number. And then we have our variable y. That is equal to 4x minus 18i. So I have two variables in this problem, y and x. Remember, I is not a variable. However, I only see one equal sign, and something we've learned in Algebra 1 is however many variables you have is how many equations you need to solve the problem. So if I see an x and a y, and that's two letters, I really need to have two equal signs if I'm to get a solution. So the fact that we have just one visible equal sign seems to be an issue. However, this is where things change because we're dealing with complex numbers. A complex number is a number that's composed of real and imaginary. And that's what we have. We have complex numbers. So there are actually two equations hidden in this problem. So even though you see one equal sign, there's really two of them. The two equations are going to be broken into the real equation and the imaginary equation. So 50 is a real number. So I'm going to keep the 50 in my real equation. 4x is going to be a real number because there's no I in it. So therefore 50 has to equal 4x. Those are the real components to this equation, so they have to be equivalent. So if we solve for x, we'll get 25 over 2. So that's one of our variables, 25 halves. The second equation would be the imaginary part, and that would be anything that involves I. So 9iy is clearly imaginary, and so is negative 18i. So we want to set those equal to each other. So again, things with I should equal other things with I, and things without I should equal things that don't have I. And the beauty of this is you got to treat I like it's just a normal number. So we can divide off I on both sides, and that kind of makes it go away. And then the equation becomes really simple. So a lot of times we see this and panic a little bit, and you just need to train your eyes to see there's two equations. There's the real part and there's the imaginary part. So this is kind of like two equations in one. In my next video, we'll go ahead and learn how to compute higher powers of I so that your workload is very minimal.